record it then for anyone else. Okay, so we could just go ahead and start with the first one. So determine if the compound is chiral. So, I mean, I just kind of looked at it recently. I automatically went to this one. I guess maybe this could also maybe be a chiral center. I don't really want to think about that right now though, so we'll just look at this little center right here, because it's connected to a Br. This one right here is a CH3. And then, so when you do ring structures, you like go down the line on like each side. So you look at both of these first and then both of these. And then this side is different. So this is one and different color. And then this is a separate one. So yes, so it has all four different like little parts to it. So it's chiral.
I would agree, I think.
Yeah. Yeah, I know. And then she didn't actually like, I watched a video on determining with a ring structure, but she didn't really tell us exactly how to go about it. Like, I don't know if like, yeah, I don't know exactly which carbons would be included. I think just those. I don't know. Yeah. But they are different because it's not like just a whole ring structure. If this wasn't here, then I think that you wouldn't really be able to tell, and I think it would be achiral. But yes, we could go over number 6 and 7. So you could get out of here. Is that on here? Yes. Okay. So we could just skip to 6. So actually, I don't think that we're able to do this one yet, right?
Yeah, I don't think we can do that, but it's going to be the same as how you determine how many easy isomers are. So it's going to be like 2 to the n power. You just have to figure out how many chiral centers there are. But I don't think we have to do that one.
So that one's not on the quiz.
No,
we haven't gone over it yet in the notes. Like that section of, there's a section of notes for that we haven't gone over. So.
Oh, okay, great, thank you.
Okay, and then for 7, so which ones could represent the entromer, right? And I hate reading it because it looks so different. Entromer, something. Anyway, so yeah, so
that one's tricky. You have to like,
I know,
manipulate the compound different ways.
Yeah. So let's see, the first, or I think the easiest one we could do is we could mirror it this way, because I already saw one that looked like it. So if you mirror it going this way, it's gonna look like that. So this is one. Yeah, otherwise, so she did this in the notes, and it's just, it would help if you label this as a hydrogen right here. So you could switch these. You could just switch like where they are. So this could be an OH in the back, and this is a hydrogen in the front. So that means the OH has a dashed bond right there. Do we have one of those? Yes, we have that for F. And then, I mean, I was trying to figure this one out earlier. And then I think it would give you the exact same thing if you like instead switched the ways the bonds were going, right? So no point in doing that.
I think there's like, if you switch the bond type, or if you there's switched bond type, switching the atom, or doing the mirror image.
Yeah, so I think that this one was the only mirror image otherwise, because mirror images, I'm quite sure, right, they always have like, they'll stay a wedged bond. Yeah, so I mean, this one isn't one. So yes, so we have those ones. I don't know about G and H. I don't know how to do that, and she hasn't even really told us how to do that. Um, yeah, I don't know if that's maybe what would happen if you switch. If you were to switch this to a wedge bond and like this one to, oh wait, whoops,
No,
this
like
one to a dash.
rotating the compound about the bond. Like if you had a molecular model and you're rotating the bond.
Mm-hmm.
So the OH is gonna, so it's not gonna look like that. It's gonna be opposite, like down, up, and then the OH on top with a wedge, I'm sorry, a dash bond. Like how, like how C
wait,
works.
okay. Saying
Like
to
if you were to
rotate it that
rotate it.
way-ish, right?
Yeah.
So I think it would look like, did you say it would be wedged or dashed, the OH? Uh-oh, that seems wrong.
Yeah,
Oh,
you drew
God.
it the same. Just draw it up, like going down first.
Oh, okay.
And then it would be a dash, like how C looks. So C, I think, would be the same compound.
Oh, same compound though? That's different then.
So it would, yeah, I'm just saying like that's how, I think that's how he wants us to do it, like to rotate. We have to learn how to rotate the bond and look at it in different, like how, like that.
Okay. Oh, okay, yeah, and if you do rotate it that way, then okay, that makes sense.
Yeah, so then you could do like the mirror image of that one, or changing the bond like to a wedge and dash and that.
Okay,
because it's the same
compound. It's the same compound. We could use. Okay, so then.
So like B would be the mirror image of that new one you drew.
Okay. Yeah. So let me just write that here. So. Okay. And then I'll leave this hydrogen here. Okay, so for this one, we said, yeah, so B would be, you could do a mirror image. Oh God, I hate doing them. Yes. I guess exactly what B was, yeah. So that's one mirror image. That's the same compound. Okay. And then this one is not one of them. Okay, so how do you feel about G and H then? Is that like anything that we're even doing?
So you can actually rotate it to make it look like G also.
Oh, okay. So is that also the same compound, or is that?
So G would be the same compound, and then I think H is the mirror image of it.
Oh God. Okay. Yeah. Okay. How do we rotate
Wait, I have a
this
question.
one?
Why is G the same compound again?
Yeah, I also kind of want to figure that out because I don't know how to rotate them like that, I guess.
So from the original compound,
yeah, so it's this one, right?
Or so
or
that
that's
the
rotated
tail,
from this
so
one.
that ethyl is, or I'm sorry, it's gonna so the methyl attached to the right of the hydroxyl, you just rotate that down, and
okay,
it's gonna be cis compound with the OH on top.
Okay. Okay. So you said you rotate this one down this way. Oh, okay, yeah. I see how that would kind of turn it. Okay. Yeah, because that pulls basically like this one goes up and then yeah, it's pointing backwards.
Oh, okay, got it. Thank you.
Yeah. Yeah, I guess I'll leave this one. I don't know if that's more confusing or less. Okay. Oh, okay, but then you're saying, okay, yeah, but this one is a mirror image of this. So. Okay, that was difficult. Thank you, Chelsea. That was cool.
And I don't know if she would, I don't think like flipping it like a pancake the other way. Oh no, that gives you the same as C. So there you go. Yeah, I think we got them all.
Yeah. Okay, wait, let's see. Questions. So yeah, someone says I thought the original only has one intromer.
Yeah, but
It's like-
we did different rotations, so
Mhm.
those each have their own enantiomer.
Yeah, I think it's like you can only like pick one, but you could make an intromer multiple ways.
So that's the thing, like, I don't know if she would want us to because that's what she did in the notes. Like she kept
Mhm.
rotating them around and was like, these are enantiomers of this. And so like, I don't,
Mhm.
so I don't know.
Yeah, I think there's just multiple ways to form them, but once you pick one, there's not another enantiomer of that one.
Was this chapter 5 or chapter 6?
This is chapter 6.
Chapter 6. Okay.
And then
So
are
would
we
it
allowed?
just be like F and so you're saying like maybe it's only F and I guess it could only be F because there's no mirror image of
For which one? Wait, what? Okay.
because I think what I did is right. I just don't know if that's the answer she's looking for.
Were you responding to one of the questions or something?
No.
Oh, well, I'm confused. Oh, okay, just kidding.
No, that the
I-
enantiomer rotating the bond is just
To find another form of the same compound.
so
That's
it's
not a way to get an enantiomer.
it's not really how you get an enantiomer. This one is really tricky for me. This chapter
Mhm.
not
You
too
did really
complicated.
good. This is very helpful. Never mind, I don't want that there. Anyway, yeah. So here, I guess we'll write little notes. So this is a mirror image, and then this one, we okay, and then B came from rotating the bond over here. Yeah, and then also rotating the bond here got this mirror image. Yeah, that one is very tricky. So yes, I feel like no, I don't want to jinx anything, so I won't say anything. But yeah, we could try that again later, maybe too. But yeah, okay.
Would
so,
So wait,
uh-huh.
what does diastereomer mean though? I'm guessing
Okay.
I keep looking at that example on where she like did the 4 drawings and there was like A, B, C, and D.
Yeah.
So maybe
Yeah.
so are those diastereomers then too? So is the other ones by rotating the bond we're creating diastereomers?
I took the diastereomers. Okay, wait, let's look at this one and this one. So in this one, okay, I took it. No, now I'm confused because they also switched places for these. That's ugly.
Yeah, but only
What about these?
only one switched for the diastereomer.
Okay. Yeah, okay, wait. It's just because the only way that I'm understanding them right now is basically that one of these is changing, but the other one is not. Because
Yeah.
enantiomers are when they both change. So if this one was also wedged, then it would be an enantiomer. So I mean, I see that part.
Like, okay, well, they would have
so-
to be also the, because if it's same,
Oh, wait, whoops.
I just get so confused. Let me look at the,
Yeah. So
there's a section in the notes. It's,
but this is only when they're in the same position, I guess. So also like these corner ones, only one of them changed, like being wedged or dashed. But when it comes, like they're changing places here.
because she did
I
like
guess
a,
it's still the same thing. though.
she made like
Oh.
an E where she rotated the bond for C and made it like a cis compound, and the Cl was wedged and the Br was dashed. And she said that E and C were still the same compound.
She
I'll
made
take
an
a-
E. Wait.
I'll take a picture of what, yeah, she wrote it, it's not, she wrote it like on the side. Let me, I'll take a picture of it and post it in the notes.
Discord or yeah, okay.
It's like a
Okay. Yeah.
small little. So that's,
Yeah. Hmm.
so that's why I did that,
It's-
because that's what she did there and said it was
Mhm.
the same compound, even though they were.
Mm-hmm.
So I just loaded
Yeah,
it to
and
the
then
note.
where did it go? I was also looking for it like in the book, and distereomers is basically just like anything that isn't an enantiomer or the same compound. It's just like a leftover thing. Let me see. Oh. Okay. So E. Okay.
Yeah, and then she rotated it. Well, the original one is
C.
the
Yeah.
cis, no, the one above it with the BR, it's the cis compound with the BR dashed. I don't, can you not see that in there? It's right above
Oh,
E.
just kidding.
That's what
Just
she
kidding. Okay.
rotated. That, so she made that compound and then rotated it to make it look like C.
Okay. Is it? Okay. Is that right? So wait. So she's saying, which way is this rotating?
Either way, she just rotates the BR bond.
Okay. I guess. Okay. Yeah. So what was her point with it? So these
That
are
E
the
and C
same
are the
compound,
same
I see.
compound.
That E and C are? Yeah.
Yeah.
Oh.
So if E and
Oh.
C
Okay.
are the same compound,
So are you
right?
saying
Like
like
wouldn't
generally?
E and, huh? I'm sorry.
So are you saying generally, like, are you saying that because like the way that this one looks, how it's like a different shape, it's like one of those?
Yeah,
whatever.
well, how like she rotated it, even though the bonds are different
Mhm.
from the rotation, it's still equal. It's the same compound as C. So if it's the same compound as C, it would be an enantiomer of D. But like,
Oh,
you know what I mean?
yeah.
That's what
Uh,
I'm
I'm just
taking
kidding.
as.
Yeah. Oh, okay. You're talking about that for like the last problem we were doing
Yeah, so that's why I was
as a reason to do that. Okay.
rotating the bond, because that's what she did there. And I mean, that's where I got that from. So
Yeah. That
where I'm
makes
confused.
sense. Let's see. I don't know if she would do that to us. Yeah, that makes sense. And she did teach it that way, so that's interesting. Wish we could ask her.
I
Okay.
know, and I couldn't make it to
yeah.
office
Well, it
hours,
says
so.
which ones came from this original one, because it says select all, so I guess there could be like just a couple, but
The only
most of
one
these.
that would, if we didn't do like rotating the bond, the only one it could be, I think, is F.
D. Oh, wait. Oh yeah, F and D then.
I don't think D either.
D is a mirror image. Yeah, from like.
Oh yeah,
this
it
way.
is. The D is a mirror image. Yeah, you're right.
Yeah, that's interesting. That could be a well.
Too
Does she
simple.
answer emails? Has anyone tried to email her before?
She answers them pretty
Wait.
quickly if you email her.
I feel like there were multiple people talking. Did anyone say if she answers?
I've emailed her before and she responds pretty quickly.
Well, maybe we could just ask her that then. If we're able to rotate the bond to get new enantiomers. That makes sense. Okay, so
Maybe you can, because D, I didn't find it doing the mirror image of it, even though it is. I did like where we flipped it and the OH is dashed on top and just did mirror image of that one. Or did the switch the bond with that one.
this one? Oh, yeah.
Yeah.
Yeah, I guess. Yeah, you could do either
So
way for
I-
that one.
So I don't know.
Um,
So maybe you can, because it's all the same. I don't
yeah. Oh, whoops. Did I spell that wrong? Probably. Okay. I'll ask her that later. Okay then. Okay. So maybe I'll put it in the Discord if she responds. But for now that seems right. Because she does give us the option of like, yeah, that. But at the same time, she's like, there's only one. I don't know.
Well, so that would those, so like G and H are the pair of enantiomers. I think those they're still paired. They're just, there's different ways to write the same compound because they rotate.
Mhm.
I don't know.
Yeah. Okay.
That part confuses
Yeah, I'll
me.
ask her and I'll let you guys know. Okay. Well then, yeah, we could go back in order then. So to determine if the compound is chiral.
Could you go up to one so I could quickly copy it?
Yeah. So that one, I mean, I just looked at this one because that's the one that I was drawn to initially, and they all have different like little attachments. None of them are the same.
Oh, because it has the 4 groups versus 3, right?
Yeah.
Okay,
For
thank you.
different groups, yeah. Okay. So then for 2, determine if it's chiral. So we have Br is 1, and then we have a hydrogen. And then here, so what you do from the video I watched is like you go down like once on each side to see if there's anything different, and there isn't. So I mean, I don't even know where I would circle. No, just kidding, because I would split it up unevenly. But actually, okay. In the video I watched, they went like all the way through or whatever on both sides. But they're the same. So it's achiral because there's only 3 different groups.
That one's confusing also.
Yeah, I know.
Because wouldn't one have one extra carbon?
Honestly, I
no.
don't know how they start.
No, they wouldn't. They'd be the same because it doesn't have a internal plane. It's not symmetrical because the BR and the H.
Yeah.
Or can you, or does it? Because you're going through the bond because you're going through the atoms.
No, I don't think it was because with the.
Because it just means BR is on top and H is on the bottom. So you're just like that's where it's folding. It's not like it's meeting the other end of like how. You know what I mean? It might.
I think, well, because I guess you could say you could cut it like in half of like the BRs and the H, or you could like split them in half that way.
Let's
But
see,
I think if
on
you can split them
page-
like this and they're different, then I think it's still not
Because on
symmetrical.
page 6, she has it, the example, like this methyl cyclohexanol. It's going through the CH3 and the OH, and like there's still a dash wedged
true.
bond there.
That's true. That is true. Let's see. Those ones. Oh, but those ones were still both achiral, so I guess that's fine.
Yeah, because if you
Oh,
fold it
okay,
in half at that
'cause-
plane, it's the same. So I think maybe it have an internal plane of symmetry.
Okay. Well, I guess either way, it's achiral, even if it does have the internal plane of symmetry. But I thought the plane of symmetry meant that it was meso. Or that's only when it has a chiral center, because I guess maybe these ones don't. Yeah, because either way.
Isn't
gonna end up there.
miso when you have two?
Miso? No. Could you explain miso better? I have this bit.
So it's saying like it has a chiral center, but it's not
Mhm.
chiral because it's symmetrical if you were to fold it in half, or and if any way you could fold it in half and it's symmetrical, then it has an internal plane of symmetry. So that
Mhm.
just means that so meso compounds just have no enantiomers. That's really all that means.
Yeah.
So it has a chiral center, but it's achiral because it's symmetrical if you were to like fold it in half. And so it would have no enantiomers.
Okay.
So you can't like get a mirror image of it and produce an enantiomer basically, because it's going to be exactly the same. The mirror image will be exactly the same.
Okay, yeah. These ones are meso compounds. So yeah, and it's symmetrical. Yeah.
This one's really tricky. I'm not a fan of this.
These ones are weird because I don't know why. Oh, because it's not a chiral center. Okay, that's fine. And then I guess. Oh, okay. And this one is a chiral center because if you go this way, then you end up at this one. Or, oh no, if you go this way, you end up at this one faster. Okay. Yeah. So miso has a chiral center. And a plane of symmetry.
So that makes it achiral and no enantiomers.
Okay.
I mean, that's just how I'm understanding this stuff. I really,
Yeah.
I'm totally
It
not
helps.
confident about this chapter.
Yeah. I think it would be good to find a video on, or definitely on meso compounds for me, I guess specifically. But yeah. But yeah, so for this one, yeah, you could also what did I find? Where's this video? Maybe I'll link it. Yes, I will. Okay, here we go. So I'll put this video copy in here. So this is a video talking about how like you go about seeing if like a structure like this is chiral, or just a solid ring structure, or if it has like something coming out or anything like that. And then meso compounds have chiral centers. It's a whole molecule. Yeah, they're achiral because they're symmetrical. Yes, yeah. So this one is like the same all the way down, and once you go all the way around. So yeah, it's achiral. Okay. Is that one okay?
Yeah, I got B as well.
Okay. So determine the appropriate configuration for this structure below. Okay, so I guess So I don't know if I should like ask questions. So I guess yeah, which one's 1? Okay, this one's 1, and then let's see. This one, I'm just gonna go ahead and say this one's 4 already because it has H3 and these ones are H2s. This one has like 3 carbons in a row, so this one will be number 2, and then this one will be number 3 then. So, and then, so our number 4 is dashed, which means, let me see, I just have it like in a note. So if 4 is dashed, no, wedged, you reverse the direction. So 1 through 3 is going this way, but we're gonna go the other way. So that is the way a clock goes. So which one's clockwise, R or S?
R.
And then I think, yeah, I was looking up a video on this one time and it said that S is kind of like 2 C's, so it's counterclockwise. Yep. Cool. So yeah, so that's the rule for that one.
Can you explain how you determine it's going clockwise?
So because you number them in order of priority. So we said this one was 1 because priority goes in order of atomic number. So this one has the oxygen, so that one's already going to be 1. And then these ones are all like CH somethings. So basically the longer carbon chain is going to have the highest priority out of like all carbon chains because it'll constantly be attached to carbons instead of like this one's attached to 1 carbon and then another carbon and then it's hydrogen. And this one's just 1 carbon and then hydrogen. So yeah, so the first one was the OH, and then the second one is going to be the one with the 3 carbons, and then the third one is the one that's 2, and then the fourth is the one with only 1 carbon.
Okay, thank you.
Mhm. Okay, cool. So that's 3.
And you said for S, it would be counterclockwise, right?
Yeah.
Okay,
S looks like 2 C's.
got it. Thanks.
Yes, if you can recall. Cool. Okay, yeah, so that one's 3. So I could probably do the fourth one. So determine R and S again. So so I have a periodic table in front of me. So again, it's by atomic number.
Brown means number 1.
Yes. Yes. Okay, sorry. There's a different one where it isn't. Okay, so this one's 1. And then chlorine is going to be 2. And then hydrogen is always like 4. And then this carbon ring is going to be 3. And then you basically just look at like the rules for these naming things. So if 4 is solid, then you could basically ignore it. So so this is going to be going in this direction, and that direction is clockwise. I literally always forget. So R is clockwise. Is that one cool?
Yeah, I also did the thing where you just like switch the hydrogen with the dash bond, but it comes out the same way basically.
Yeah.
Well, you don't switch the atoms, you just switch the bonds. Sorry. So like
Okay.
hydrogen will get the dash bond, and then the bromine will get the solid line. They don't
how
trade,
does it,
they don't trade
Ooh.
places, they just switch their bond type.
oh, how does that change? Well, I guess it doesn't, but
It doesn't, it's still gonna be clockwise.
oh, is
It
the
was just
answer?
the other option
Oh,
she
and then
had.
she tells you to go by like the dashed thing instead, which is to record the direction of 1, 2, and 3. Yeah, so basically it's the same thing.
Yeah, but I didn't even realize that you just could just ignore it.
Yeah, I know.
Because she did the Newman projection thing, and I hate those things. I don't understand
Yeah.
it. So I was like, I ain't doing that.
Yes, unnecessary. Yeah, you could just ignore it and then just do 1 through 3. Yay.
Cool.
Cool. Okay, so that's 4. And then again for 5, I hope it's just a bunch of this. So again, I'm looking at a periodic table. So I has the largest atomic number, and then it's Br, and then it's Cl, and then it's chlorine. So dashed is, oh wait. Okay, cool. Yep. So again, I guess I'll pick different. Going that way, this way is still clockwise.
For this one, I'm a little bit confused because we record the direction from 1 to 3. Does that mean you just ignore 4 again?
Yeah, basically. Wait.
You're not
Yeah, because
really
I think
ignoring the 4, because like whether it's dashed or wedged is important. The number 4 that you label.
Mm-hmm.
So that's how you determine, which direction you're gonna go. If it's gonna be clockwise, or you have to do like direction and then reverse. But you're just counting the 1, 2, 3 atoms when you're figuring out the direction.
Okay.
yes.
But the 4 matters in how you know to go about that, basically.
Okay.
Cool. Okay. So cool. So that's 5. Cool. Okay. And then we did 7. We'll see. Okay. So 8, determine which have a diastereomer relationship. So yeah, so for this one, I just go with the easy ones first, because let's see. This one, easy one, because only one of them is different.
Mhm.
Otherwise, let's see. So this is definitely an
Those are
enantiomer. Oh, what about these ones? I feel like, or well, I guess it's
only 2 changed. Yeah. So I think that one.
So it's
Oh.
also an enantiomer.
No, I think it's because you have to change all of them. So that other OH would have to be a
Oh.
dash bond or a wedge bond. Sorry.
Oh, maybe that's just because we've only done it with 2.
I think because we wrote down only some change for diastereomers, but all of them have to change for enantiomers.
Oh,
That's just what I'm going off of.
okay.
And then also I circled A because it says that diastereomers are cis and trans isomers. So I just.
Okay, wait. Sorry, could you repeat that?
I also circled A because like the first, well, when she says that it says that diastereomers are cis trans isomers, basically.
So
I
that would be
circled that one
helpful. Is that
faster.
true? Diastereomers are cis trans isomers.
Well, B is
That's
B cis
helpful.
and trans.
True.
Well, cis, but D can't be cis and trans because there's 3 atoms, but it would be either E or Z, which is kind of the same thing, almost the same thing as same meanings as cis and trans.
Okay, yeah.
But that's just my logic. I'm just, I don't know. I can't confirm.
Yeah.
Why is it not C though?
Because
C,
both of them are changed, so that would mean they're enantiomers.
But if you look at the example on page 6.5, she compares A and C, and they're kind of, oh, wait, no,
Oh, that's okay.
hold on.
We'll look anyway. Oh. Sorry. Yes.
You mean A
so-
and C or A and B?
Hold on. C and B.
C and B are diastereomers. That's cis and trans. So only one bond, only the BR bond changed from a dash to a wedged, but the CL stayed as a wedged.
So there's diastereomers.
Yeah, so if both the BR, so if BR became dash, I'm so sorry, if BR became wedged and then the chlorine became dashed, then that would be an enantiomer, like how it is for A, because they both of the bond types changed for the group atoms.
So they're diastereomers.
A and B are enantiomers because both bond types changed. If only some of them changed, like
No,
so
not
like
A
how
and B,
C-
C and B.
Yeah, C and B are diastereomers. Yes, yeah.
But wasn't that what question 8 is asking though? Compounds have a diastereomer relationship. So if you look at C and B, and then you go back to question 8 and you look at C, they're kind of similar.
Not
Or am I
A
looking at different?
on the number 8 for A, you're saying?
Number
or the-
8, letter C.
They're both changed though. So both of those wedge bonds became dash bonds. So if they were diastereomers, only one of those wedge bonds would have became a dash bond.
Oh, okay, I get what you're saying.
Yeah, this chapter sucks.
Yeah. I still hate this. She hasn't.
The only one, yeah, that's
Whenever
that
they
was just
rotate
my
these.
logic, but yeah.
Mhm.
Well,
Yeah, this one.
because you can't rotate an alkene. That's why they're cis and trans, because they're isomers. Because they, they're not the same.
Yeah.
Because they can't rotate.
Yeah, I'll look at that one more later and then try and like make it make sense. Fully. That's cool. Okay. Well, that's it for the first one then. Yeah, we just have. Yeah, I want to figure out 8A, and then I'll email her about 7 to see if that's what she wants us to do. Okay, then we aren't doing 6 or anything. Okay, so we could do the next one then. Or did anyone want to do anything else on this first one?
Whoever asked the question for number 4, 4 is A, it's R.
Oh yeah.
I had a question about number 4. I actually got S for that one, but I wasn't sure about it, so I just wanted to double check. I tried to look at it like a Newman projection first, because I wanted to learn both ways. And so if I drew the I coming from the bromine with the hydrogen in the back, then it would be the bromine on the top right, chlorine on the top left, and then the bottom thing would be like the ring.
Okay, wait, let me see. It's like where I drew the I, right?
I think she drew the I
the
from
same
the
way.
other side.
Yeah,
just kidding. Oh, are you
the
supposed to draw it from other
dash.
side? Just kidding. Okay, well then, yeah, that makes more sense. Let's see.
But when I did that, I got I might just be mixing it up because you know how it gets kind of convoluted with the whole like, oh, then you have to switch it back. But
Yeah, let me see. If that's
it was
towards the
counterclockwise,
end.
I thought.
Okay, great. So and then the priority. So this one's 1, 2. This is
Wait, your
uh-oh,
projection
yeah.
is your eyes on the other side then, if that's how your projection comes out.
Yeah, I was looking for this one for a second. Ugh, wait, okay. Or this is 3. Okay, wait. So in order to get those ones. Okay, so the eye has to be right here, right? Looking in there.
No, your eye is facing the chlorine because your hydrogen's at the bottom, right?
The hydrogen is supposed to be hidden behind the Newman projection so that it can be like a dash
Yeah.
bond.
Yeah. So did you do it this way?
Yeah, like looking
Like
into the
that, okay.
hydrogens, but the
Okay.
bottom would just be the
Oh,
the
your ring
ring.
is on the bottom. Sorry. Okay. The ring's on the bottom.
Okay, yeah. Okay, yes. Anyway, so then this is 2 this way and 1 and 3. You got this way.
Yeah, but then after that, if
Yeah.
we do it like that, do we have to switch the direction or do we just leave it how it is in the Newman projection? That's what I was a little confused on. Sorry.
Because I don't really do with the Newman projection. We were kind of talking about it because that's how she said to do it. Because I'm pretty sure I drew this right too. 'Cause
give
if
me a
you're looking
second.
this way.
Because maybe the
Yeah.
bromine and the chlorine are on the wrong side. Give me a
Yeah,
second
maybe, but to create it.
give me a second. Yeah.
Yeah, I'm pretty sure they aren't because it would be on your right. Yeah, if it's coming towards you.
So if you're
That's a
looking
little annoying.
this way,
Yeah.
okay, so you're this is in the back. You're looking at it like this.
Yeah, but yours literally is this way when we got it going the other
At
way.
it. It's so I hate this thing.
But then when
That's down.
I kind of gave up on this because Newman directions are weird. So then I tried it again, but I followed just the directions I gave in the note. So I did I swapped the H in the bromine because you swap the priority 4 with the
Oh,
wedge
yeah.
one.
Or
And
is it?
even then I had gotten that it was S, but I might have messed up and I feel like I'm just getting myself confused. So I'm sorry if I'm wasting time.
No, you're good. Was that what she? Here, wait. So let me do the priorities
yeah.
again. So this is 1 and 2, and this is
The
4
ring on the bottom.
and 3.
Oh, let me look at that. In the back. So we're looking at it.
Didn't wait, Chelsea?
I
What
just
were you saying about? I thought when 4 is solid, you change it to, or you switch the bond type with, so it's dashed, and then the chlorine is straight,
No,
right?
you change it to a wedge
That's the
bond.
one. Oh, you change it to a wedge. Oh, okay. And then this one's straight. So then,
So BR would be straight. H is
and then you
wedge.
have to follow the rule of that, which is, okay, yeah. So what
Well,
is
I
the
thought it
Newman
was you
projection
swap where
thing?
the atom was, not where the bond is, or like where the bond type is.
I thought it was a bond. I remember something about the bond type, but I haven't been doing it that way.
So it says swap the priority number 4 with the priority group attached with the wedge bond. Then determine and record the rotation direction of the new priority
Oh yeah.
arrangement without reversing the number
I think
4.
you do switch the atoms, not
the whole atom.
You
Okay,
switch the
so
atoms, not the bonds. Yeah.
hypothetically, okay, so hydrogen here and we are
Because
here.
also I think with the projection, I think she is right that I think the bromine is on the right. I'm not good at those, but I think.
Oh
I
wait,
think-
so then are you also getting S for 4 then?
I think I'm also getting S now. Yeah.
Oh shoot. Okay. Okay. This, hold on. Okay, I'll just you guys for now. Yep. That's okay. Okay, so in the notes. Okay, wait. So what is the note about this one? So
So you would switch. You're switching the atoms. So you're switching H and Br. You're swapping them. So the atoms, not the bonds. Or bond type. Sorry, I don't know. It gets confusing, all this language.
It's so weird. I don't like this chapter. It's very visual.
yeah.
Well, learning the molecular models online isn't very easy either. She I don't know what she thinks she's showing us, but it's confusing.
Okay. So yeah. Okay. Yeah, and then just for that one, you go in order. Okay, then. Wait. Oh, okay, but you just go in order of 1, 2, and 3. Okay, that was confusing. That's cool. Okay. So then, oh god, where did this? Okay. Okay.
Nice save.
Not my
Not
method.
sure who
ever
brought
again.
that up.
Yeah.
Save.
Thank you. Cool. Perfect. Okay. Well, then I guess I'll be doing Newman projections again. All right, cool. Okay. Yeah, so 4 is actually as you do the Newman projection, or if you go by the rule, it's that when 4 is a line, you switch the number 4 atom for the wedged atom.
I still think that's the easiest than the Newman projection. I just did it in the wrong order. I switched the bonds
Oh, yeah.
instead of atoms.
Yeah, that's cool. Okay. Cool. Okay, so that's this one then. Any other things for this one? I didn't mess up any other one, did I? I don't think so. Okay. Okay. So we could go to the other one. So for this quiz, we haven't done this yet, right? For one, how many chiral? Well, I guess we could. Maybe we have.
I mean, you're
Of
just
course,
finding
okay.
chiral centers, right? I think.
Yeah. This isn't one because those are the same thing.
I only put
Um,
one.
Yeah. So. Oh, frick, I should have not done that. Okay. 2, and then, yeah. I don't even know how it works for these, but yes, something like that, maybe. And this is a whole different one.
Well, all we know is one carbon will have 2 carbons attached to it, so it's not even either way. One will have like those 2 carbons, and then a
Yeah.
third one, and then the other one just has 1 carbon attached,
Yeah.
or atom, whatever. Either
Or,
one carbon's
yeah,
gonna
whatever
have one.
this is different than whatever this is. And
Yeah.
that's the truth. All right, cool. So just one. Because this one, they were the same thing, so not that.
Yeah, I guess maybe we should ask her how to label priority when it's a ring, because we don't have examples like that in the
Yeah,
note.
I know. Yeah, I don't even know. Okay, cool. Okay, so
For that one, the chiral ring is the one that's in purple.
oh,
The blue asterisk. Oh,
yeah.
The asterisk, okay.
This is just the other little group.
And that's because it's different than the 2CH3.
Yeah, so that's because I mean it's like I'm just drawn to like wherever these things are, the wedges and dashes are, because like you could have one here, you could have one here. You don't have one here because these are the same thing.
Mhm.
And then you look at this one, which is just this carbon here, and then it has 1 CH3, 1 hydrogen is also there. And then when you go over one on either side, this one is going to have all these things attached, and then this one's just going to be like a CH2. So they're all different, so it's chiral, and that's the chiral center.
Okay, thank you.
Okay. So then for 2, determine if it's chiral. Whoops, go here. So yeah, this one, which is different from this one. And then you're gonna have this side of it, which is CH3, CH2. And then you'll have this other side of it. And I have CH3, CH2, CH2. So yeah, they're all different. So it's chiral, right?
Think so.
Yeah. Okay. Terminus. This one's chiral. This one is gonna have another hydrogen right here. So no, right? Because it's not charged or anything. So if it's not drawn in and it's not charged, yeah, it's another hydrogen.
I agree. I think.
Alright. Okay. Determine which structures represent the enantiomer. For this one, I feel like I wouldn't want to do like any kind of rearranging it or like
No, that
flipping
I
it.
think that's just like how she showed us to draw it. So you could either switch the bond types or switch the atoms or do the mirror image.
Yeah, I guess, but this one also she kind of made it more clear, like probably not to do that. Yeah. So for an enantiomer, you can switch or you could mirror, or you could switch atoms.
But only do one or the other.
Okay, yeah.
He says not to combine the methods.
Or well, I guess I'll just do only one.
Choose
Okay.
your plate.
Yes. So this one, they just switched the atoms. So this is one.
The number 2 we said was A. Number 3 is B. I don't know if that's.
Oh wait.
Sorry, someone asked a question.
Oh, okay. Yes. This one is not. There's too much happening.
Yeah, there's two methods applied there. Oh no, that
I
one.
think that's technically like the same compound anyway. Actually.
Um,
They're just like written differently, which I don't think even matters.
it's the mirror image. That one.
Is that? Oh, it is.
So that's why the H is on the left side,
Oh,
because in the mirror,
Yeah,
it's closest to the mirror.
Just kidding. Haha, okay. Okay. This one. Okay, this is what I thought that one was, and that's not. This is
Yeah,
the
that
same
one
compound.
combined 2 methods, so you can't do that.
Okay, and then this one, they just switched the wedge bond.
They swap bonds.
Cool. Yeah. Is that one cool with everyone? Uh-oh.
For number 4, is there only one answer and it just depends on which method we use?
I think for 4, you could, there's multiple answers because, yeah, you could do it any of these ways.
But we
They're
only
different.
choose to use one of the methods, right?
Yeah,
Yeah.
I think that's when you're doing it. You stick with like one of these. But,
So those 3 are different representations of the same enantiomer, basically. You just, because on page 7, at the bottom, it tells you how to draw the enantiomers, and you would use either of those 3 methods. So the ones that we circled are each of those methods and that's how you can draw, the different way you could draw the one enantiomer.
Oh, okay. So on the quiz, would we just choose one of the ways?
Yeah, I think you would just choose whichever, unless she states to do all 3 or to like show all 3 methods, or I don't think she will. I think you just choose whichever you prefer.
Oh, okay. Thank you.
Or if it's a question like this and she'll, you just circle them or whatever.
did she say the pages that we're being quizzed on. I have them. I
It's
can,
up until the relationships.
yeah. And then we're also doing a little bit of chapter 5. She kind of made it sound like we were just doing like the H2. So it's gonna be like Lindler's catalyst and NaNH3 and that stuff. We could go over that really quick after too. But we could
I
probably
would
just,
go.
like,
I would go over the alkyne reactions because those are
yeah.
the trickiest.
Yeah, let's see. I guess
I think she's gonna have an alkyne question on there.
so. It's just starting from the bottom of 10. Yeah. Yeah. So wait, no, not this one. Never mind. This one. Yeah. I feel like these ones get pretty easy after a while though. Yeah, I guess we could go back over this one after.
There was a question, I think, at the end of the study guides for quiz 3. There was like 1 or 2
Yeah, that we
alkyne
couldn't do.
questions.
That's true.
It might
Here,
be
wait.
something like that.
Should we finish? Here, wait. Let's finish this one first, and then we could go look at that. Yeah. So yeah. So 4 is good for everyone. Interest. Okay. Okay. So 5. Which ones are diastereomers? So diastereomer, basically when you do only one thing, or not even only one thing. Okay. Let's see. This one. Oh, okay. Diastereomer. What did we say before? It's like when you
Only
change
some,
some, but not all.
yeah, only some bond types will change. But you can also, I mean, I've been noticing that they're like cis trans or easy, isomers also. So that's one way to think of it.
Mhm. Okay, yeah.
And it
So,
also
yeah.
says that on the first page that diastereomers are like, they're classified as cis trans and easy isomers. So
Oh, where does it say that?
on the first page,
Of
beneath the
notes?
stereoisomers definition.
Let me see. Oh, perfect. Oh, perfect. Okay, yeah. So that's what I was looking for earlier too. Yep. So diastereomers are also easier cis trans. That's perfect. All right. So there's that. Okay. So this one. Okay. So I already said that these ones are diastereomers because these ones
Mhm.
change, but this one stays the same. You're saying
Well,
why?
because F didn't stay the same. One's wedged, one's
Oh wait,
dashed.
but they're diastereomers.
No, they're enantiomers. Because all of them.
No, we're looking for dice. Wait. Oh, whoa! I had a full stroke. All right, I literally lied. Okay, never mind. These
Yeah,
all
I know
change.
we're looking for
Sorry, okay.
diastereomers. Those aren't it.
Okay.
I'm just kidding.
No. Okay. Let's see. Anyway, these ones are actually the same, and these ones are actually different. So these are diastereomers. Okay. This one, I don't know, because I think that this is like whatever like the weird diagonal ones were in the example.
I think because I think we're supposed to flip this one like a pancake. So if we were to do that, then the methyl would be dashed on the right side compound.
Yeah.
So Cl would be on the wedge. I think that's
Oh,
how.
okay, yeah. So if you look at it that way, then it's also diastereomer.
So only one changed, I think. I think that's what we're supposed to do with these things. I don't know.
That makes sense. That makes
Like-
sense as to why those other ones were too. Yeah, because you could definitely just like rotate it however you need. Okay, yeah, that makes sense. So
So yeah, like you can't rotate a ring, but you could just flip it.
yes, flip it, and it's like the same thing. Uh, okay, cool. Does that make sense for everyone?
So the dash for that one, when you flipped it, that's the methyl.
Yeah. So if you were to imagine like, because this one's coming towards you, and then this one's going away, and then if you were to like, I'm doing it like with my hands. I'm like, if you were to flip it over, then the one on
So where the dashed methyl is, there would be a wedged hydrogen instead of a wedged methyl. That would be coming towards you instead, because you like flipped it around.
Okay.
If that makes sense. I know it's really confusing, the manipulating the
Yeah, the
compound like
flipping of
that.
it.
Yeah.
Okay, thank you.
Yeah, I feel like the toothpick things would be helpful for that. Or I feel like you could do it with your hands. Like here, I'm gonna turn my little camera on. Will it even?
I can't do it with my hand. I think
you
I
even
need the model to actually see it, because I get so like.
Can I
I
pin my
confuse-
video? No. Does anyone need to look at my hands? Now I don't want to do it because my camera's on, but I don't think that my face is popping up. Does anyone?
No.
No.
I can see you if you want to do it.
Okay. Well, if you have, okay, because I'm like saying that, like, I guess my wrists are like the line. So like you have, well, in this example, like in the beginning, we have the chlorine. Well, the chlorine's actually going out, and then this methyl is coming towards you. And if you were to flip it, it's gonna like the chlorine's gonna be going towards you, and then the methyl is gonna be going away from you. That was kind of gross how I did my hands. It made more sense last time. No, it's literally just.
I get it. I think
like,
that was
Yeah, I got
this
it.
way. Okay, yeah. If you turn
Yeah.
your whole body with it, yeah. Well, then, yeah. Yes. Okay. Maybe. Okay. Anyway. So yes. So that's diastereomers. Yep. Change some bond types, but not all.
I kind of got lucky on that one though, because I didn't even realize that the chlorine was in a different spot.
Oh.
So,
Dang. Yeah.
but it still worked
Oh
out.
yeah. She is.
I still was able to explain it.
Yeah. I know that was a very good idea. Flip it. Perfect. Okay. Cool. So yes, so there's 5. I think this one has less. Oh, yep, that's the last one for this one. Cool. Let me get the check again. Okay. So yeah, so that's it for 6, and we were able to do basically all of them. So we're talking about doing the ones that we couldn't do on this one before, I think. Let's see.
I think it's on the other one.
Yeah, I guess so.
This has the canvas one.
Wait, was it this one? Yes. Yes. Okay. Okay. Ew. Okay. Oh God.
I know. I had to go back real quick because I totally forgot this stuff.
Yeah.
So to make
So-
okay, so if you were just to do the metal and the hydrogens, that's would take it all the way to an alkane. So we can't do
Yeah.
those because we have an alkene as our product.
Yeah.
The NaNH2 is supposed to make the alkyne into a conjugate base.
Yeah, and it's for terminal.
Terminal.
alkynes.
Yeah. Oh yeah.
Or
yeah.
alkene. Or yeah, alkynes. anyway.
Kynes, yeah. And
So
so the H2 and Lindlar's catalyst makes a cis alkene. And the Na plus
Oh,
the
it
Na and NH3 make a trans alkene. You wouldn't do A. A is the same as B, basically. You can use palladium.
oh yeah.
nickel,
Okay, yeah.
or-
I'm also not looking
I
at
can't
the
remember
things
the
there.
other one.
I have a little cheat sheet. Let me see if I can find it really quick. Oh, okay, yes.
Oh,
It
and
goes from- okay, yes. These go from alkyne to alkene, yeah.
Alkane, yeah.
Okay.
Okay. It goes
Yeah.
to
Oh,
alpha.
whoops, sorry. I was trying to label this one. Yeah. Okay. Anyway,
yeah.
so this lady is, well, this is a hydrogen and this is a hydrogen. So they're trans. Well, this one. Yeah. So it's trans. So it's this one. Ah. Is that one cool? That might be the only one. Actually, no, there's one.
There's one on
I'm
the back.
a little
I think
confused
number.
about it.
What was that?
So why is it trans again? Like, why is it number 1 and number 1 there?
Well, because I mean, for me, this is just like the way, because you know that this one is gonna have one more thing coming out of it, and it's gonna be a hydrogen. The only way that hydrogens can go in here, like, it's definitely not gonna like come out through here. So the hydrogens want like the most space is why. So
You can
they're
also
gonna,
think. Sorry, you can also think of it as the E, because we were numbering it based off of like the easy rules. So you remember when we name, because easy is the same as cis trans, except it's
Mhm.
for 3 or more atoms, and cis trans is only for 2 groups of atoms.
Mhm.
But E is the same thing as trans, and Z is the same thing as cis. So that's how she was numbering it using the easy rules.
Oh, okay, got it.
yeah. So that's just because this is a carbon here, and carbon has a higher atomic number than hydrogen, so that one's priority. And then you like separate the bond in the middle, and they're on each side of the bond, so that means they're trans. Yeah. Okay. So yeah, so it's just basically that one. Oh, and this one. Why is this done? It's like
Yeah, that one.
for each
That
of
one I'm
them.
confused on.
Oh, actually, I think I went back to it and tried it. Let's see.
And I'm confused because in the homework, so I think you can do the first 2, like A and B,
Mhm.
but C and D. So in the notes, it says that a secondary and a tertiary
True.
Carbon alkyl halide or whatever can't.
I think
There's
that's
no
true.
nucleic
Mhm.
that's a secondary. Oh no, that one's a secondary.
Oh, which one is?
The third, where you have the 3, that's a
Oh,
secondary,
yeah.
and then the other one's tertiary. It says that it can't do a nucleophilic attack, but in the homework, there's a one where it looks exactly like C and it does the reaction. So I don't.
Yeah, I definitely do remember. Yeah, these aren't able to happen. I feel like this. Well, yeah, I'm sure that that's right. I don't. What homework? But oh, do you know?
Oh, it's yes. Hold on. It's on.
I'll just look for the answer thing, and I'll see. I guess if.
So it's on 4 point. Where are you? Where are you? Sorry.
Here.
I swear I had to go do the. Okay, it's 4 point. Nope, it wasn't that one. Sorry.
That's okay. Yeah.
Where is it?
Yeah.
No,
We're trying
this is
to
it.
find it right now, but it does say in the notes, yeah, that second degree and third degree carbons can't form, or well, they basically can't bond to this one, or they can't perform nucleophilic attack, is what Kelsey said.
How is
'Cause I
it?
could definitely find that in the notes.
I'm trying.
That's okay.
I have it. I had it ready, and then I
Oh, you
don't
do?
know.
Oh. Yeah, because you say right here. I mean, I would go with what she did.
It's 5.44. Question A.
Okay, 5.4. For a, I'm looking in the answer section already. That's annoying. Yep. It literally says it happens, but they're also wrong in the book a lot. So
But it
This
also
is-
says the product isn't a major product in the notes.
oh,
Do not
oh.
get attack product as the major product.
well then that might be true.
So I don't know what
That's
if
so
there's
stupid
some
that they even had it
underlying,
happen.
thing to that sentence.
Yeah, that's dumb. Okay, yeah, I would just go off her thing then. Yeah, because these are literally like exactly what we have in the thing. Perfect. Yeah, it's probably not the major product because it doesn't really form because it's not supposed to. Okay, yeah. So then,
This is chapter 5, Natalie. On page
yes.
514.
Yeah.
And then this
Yep,
is the and then this is the chapter 5, or sorry, quiz 3 study guide.
Yeah.
So yeah, I would say no because that's what it says in the notes, but I saw that in the book and I was like, great.
No. I trust this. Yeah, these are no. That's cool.
And why is B yes?
Because it's a
because-
methyl. It's
Oh,
a
is that one? No, wait. This one's a methyl.
it's a primary. That one's a
First degree.
methyl,
Okay.
and that carbon is primary because it's only attached to one other carbon.
Got it. Thank you.
But if there were like another thing right here, then I think it could just attach. Well, you think, wait, okay, just hypothetically, if it had one more, I would say that it would just go ahead and attach, right? Yeah, because then this one is a
well,
wait,
But that
whoa.
carbon that's attached to the bromine is still secondary.
What about this one? I don't even remember how they work now.
That carbon doesn't even matter because it attaches where the bromine. So the bromine, that's
I
where it
didn't know that.
attaches.
Whoa, I didn't
That's
know
if
that.
you connect the compounds. Yeah.
Okay, it attaches here. Okay.
So basically, you just remove the bromine and attach that into the.
Mm-hmm. Okay,
Okay.
cool. Good to know. Okay.
And
Okay.
I helps me. I draw like the line, like where you have the yes and no on the product compounds.
Mhm.
I draw the line where that bond was made because it's easier to see, like what.
Which line? This line?
So like a line through, I like a vertical line.
Oh, I don't know my vertical and
Yeah.
horizontal.
Yeah.
Oh, okay. Just to say that this is
So
the
like
bond.
that's where bonds are.
Oh, yeah. I've just been looking at it literally the easy way. I haven't even been looking at the freaking secondary or tertiary. But yeah, I was just recently looking at that again. But I'm just like, yep. Just like literally the exact same thing. Just, yeah. It just steals the bromine bond mostly, which is fine for now, I guess. But yeah. True. Okay, cool. So that's 5. And then I think there's like one. Yeah, it's just this. Is this right? This is definitely.
I put either a base or a nucleophile.
Yeah. What would be the difference? I know she said once, like.
So it's a nucleophile
Because it's negative, right?
when it's attacking like a carbocation, like when it's attaching to the alkyl halide. I think. And then it's a base.
Ugh.
It just depends on like what you're doing with the reaction.
Yeah.
So like,
Whatever. Yeah. Yeah. Nucleophile, I thought because it's negative, and then the base. I don't
Yeah,
know. I feel
but
like
she
they
also
just
said
nearly always have
nucleophiles
both.
are the same as bases. Well, like that's what they
Yeah,
add
exactly.
in the Lewis acid reaction.
So they can't be one or the other, right? I don't think so.
You'd have to, if
Or, well, I
she
guess
gave
you
us
could have
a
a base.
whole like equation, then maybe we could determine if it's, but she's just giving us the terminal
Yeah.
alkene. whatever.
what
So.
would show that it's a base?
The negative charge.
Oh, so that's not for a nucleophile?
It also is a nucleophile, yeah. So
No.
it just depends on in your
Oh.
reaction what it's doing. It's kind of hard to explain. But so like what I'm interpreting is like if it's reacting with an alkyl halide, it's gonna be a nucleophile because it's gonna attack I think alkyl halides are because they have like a partial positive charge. So the negative charge attacks that partial positive charge. But if you just have like a basic acid base reaction, you just have an acid and a base, like it's gonna just be a base.
Okay.
If it's not, it's kind of hard to
Yeah.
explain that.
Yeah, their definitions basically overlap, so it's kind of whatever. I guess you could just be both at the same time because nucleophile is electron rich. It could donate a pair of electrons, which is like literally the definition of a Lewis base. So it's whatever. Yeah. In these cases, they're just probably gonna be both. Yeah. So that's this. Or well, that's all gonna be on this quiz.